if not all of you. And this is obviously a new development. It's to replace the SDR, and this is currently the only one of its kind in the world, and probably will remain so. But this is the world's first and only SFR. So what we're talking about tonight, well, we've got the radio here. You can have a look at the radio later. So I'm going to talk about the problems with software-defined radio, explain what an SFR is and why it's so much better, show how it works, how I built it. It's taken 40 years to build, so I might demonstrate it a bit. We've got a bit of wire running down to the flagpole, which picks up all the computer and network noise very nicely, so I can demonstrate it receiving noise. So, problems with SDR. So there's lots of problems with them. I mean, there's millions of them around. I don't know how many models of SDR you can buy that you could use on the amateur bands, but it must be 100 or so. And they all go out of date very quickly, which is frustrating because you spend a lot of money on one and then it goes out of date. And they're quite difficult to use, as you're probably all well aware. The functions are all buried in menus. So if you hear some exotic DX station and you want to adjust the RIT, you've got to dig into menus to find the RIT, and half the time you forget which menu things are in. And if they're difficult to modify because it's all software defined, and if you can't write software, you can't change the software very easily. And also software, especially these days, it's got so complicated it tends to crash, or it does unexpected things. You press a button and the wrong thing happens because there's a bug, or the person who wrote it's got a different idea about it. So there are problems with SDR. It's certainly got its good points. I'm not entirely knocking it. So the solution. So I've got this new concept in radio called the software-free radio, and it gets around the problems with the software by not having any. So it uses hardware for all the functions. You can make a whole radio, you probably wouldn't believe this, you can make a radio using hardware. And the controls, rather than menus, it's got this new concept called knobs and switches. I'll come back to them later.
No buttons.
It's got a button as well. It's a sort of button's a sort of switch. And it has lots of advantages. So all the controls are just there. So if I want to turn the audio gain up, there's a dedicated knob to it, and all that knob does is audio gain. So I can turn the audio gain up, and so on. So you don't have any of these problems digging through menus. Now, you're probably thinking, how would you do filtering without DSP? And the answer is you can pass the signals through rocks. And I've got an example here. These are commercially manufactured, or they were in about 1970. And there's about 8 rocks in there and a couple of capacitors. So I'll pass that round for those who haven't seen them. I'll start with you, Andy, because you know these very well. You've got a box full. So, as I mentioned, the trouble with software is it's very difficult to change it, because if you can't write it and you haven't got the source code, you can't change the software. With this thing, it's fully reprogrammable using a soldering iron. If you don't like it, you just change the circuit. You just need the soldering iron. So it solves all that problem a stroke. And the other problem, as I mentioned, was obsolescence. You buy a very nice SDR radio, and it's obsolete in a year. This, it's no problem, because it was hopelessly obsolete long before I even built it. So I don't have to even think about obsolescence. It's all built in as standard. So, rough specification. What does it do? It covers all amateur bands, 1.8 to 30 megs. It's not got general coverage receive, which in some ways I like, but I did that to simplify it. It took 40 years to build, and I thought it would have taken a lot longer if it was general coverage receive, so I might not live that much longer. Covers CW, SSB, AM and FM, which are the modes I'm interested in. You could do data modes by putting audio in, as you could with any radio, but it's basically all modes. Receiver sensitive, about 7 dB noise figure. Intercept points 14 dBm, so it's got plenty of strong signal handling. Now all the broadcast stations gone, I think it's better than you need most of the time. And you've got a choice of bandwidths from 8 kilohertz down to 150 hertz for different modes. It was designed to be used in the shack and portable, or sort of semi-portable. So it's 20 watt output, it runs off 12 volts. Because I could run it off a car battery or whatever in the field, and if I want to use it in the shack and need more power, I just build a linear. It's got braking on CW, which I must admit I don't really use, but it's got it. And there's a speech processor for voice modes, which is also the club project. That's where the club project comes from. It started with this thing. Birdie? trying to pass through a crystal filter.
Sorry.
Not the most interesting things, is it? It's supposed to be competitive with a modern radio. It's not quite there. It's not got things like band scopes yet, so there's some boxes to add on to do that. Right, so what started me building this radio? Well, when I was about 17, I was starting to get into amateur radio, and I thought it'd be great to build my own station, and couldn't really see an easy way of building a multi-band HF rig. There were no sort of designs I like the look of in magazines or anything like that. Licensed in 1985. I remember riding a bicycle along the Highlands Road, and I thought, I know how to do it. And I knew about tunable AF radios. And I could make crude synthesizers, but not a decent one tuning in 10 Hz steps. So why not combine a crude synthesizer and a VFO, because VFOs are easy to build. And about this time, Mick G0AMS, this chairman of the club at the time, he'd worked at Plessey's at Wesley, and they finished a production run of a comms receiver, and there were loads of those crystal filters looking like that, kicking around, and he sold them at the junk sale for 10p each. So I bought a big sack full of them, and he gave me a load later as well. And I've since acquired a few more at Horndean junk sale. So I've had this big box of 1.4 megahertz crystal filters kicking around in my junk box for decades. So I thought I ought to use those. So it took about 40 years. I mean, I've got early versions here. This version's about version 5. This is about 1999. That was the IF strip. It did nearly work, but I got fed up with it and gave up. That's all built with leaded components, and it's just a piece of copper clapboard and hand wired underneath. I'll pass it round if it's of any interest. That's about 20 years ago. I was actually going to publish the design for that if ever I got it working, but it never quite worked well enough. But that was the plan. So tunable IF. So it's a very old technique. The earliest receiver I can find using it was a Collins 75A1, which is about 1949. So it's my sort of vintage, perhaps a bit modern for me. What does it do? So if you think of the old radios, AR-88s, HROs, the sort of wartime vintage stuff, you had an LC oscillator that did all the tuning. And when the set worked up to 30 megs, the oscillator had to tune up to 30 megahertz, so you had difficulties with drift, you had problems with band changing, you had poor readability of the dials. I mean, a lot of those old sets, the dials are calibrated to about half a megahertz. The B28 certainly is. So on 28 megs, you can only read your dial to about 500 kilohertz, which is not really ideal for modern amateur work. So Collins made very expensive radios, and their solution was the tunable IF. So I've got an example here. The figures come from what's used in this set. They're not actually the Collins ones. So if you imagine the set tuned to 20 meters, so you've got an aerial, there's a bandpass filter that covers 20 meters, and then there's a first mixer, and that's fed with a crystal oscillator. So there's a different crystal switched in for every band, more or less. So that converts down to this, what they call a tunable IF. So you've got this bandpass filter, in this case 5 to 5.5 megahertz, and this is fixed on all amateur bands, doesn't move. And there's a second mixer and a VFO, and the VFO is on a reasonably low frequency, so it's easy to make it stable. It only covers 500 kilohertz, so you can have quite an accurate dial on it. And this, you get the same dial on all bands, same dial resolution. You can, on the Collins set, you might be able to read it to a kilohertz or two, that sort of accuracy, so it's starting to look usable. And you just switch crystals in and filters for different bands. And that works great. Obviously you convert down to an IF, in this case 1.4 megahertz, and you've got crystal filters and IF amps and your detectors and all the rest of the radio. And it works very well. These Collins sets are still good, and the Drake 2C used it. Another very high quality radio. The FT101, the older FT101s, pre-Zs, so the FT101, the Mark II, the B, the E, that series, they were all tunable IF. The IF was about 6 megahertz on those, and they're very good radios. You can still use them on the bands today quite happily. Edison EA12, very highly respected set, that's tunable IF. So that's the basic principle. What have I forgot to say about it? It died out in the mid-70s. They started to be able to make high-frequency crystal filters. So rather than have this wide filter here that lets a whole band through, you could put a crystal filter in here and just look at the channel you wanted to. And that has the advantage that this mixer and anything downstream is protected from big signals. So if you're operating on 14.1 megahertz and someone down the road is operating on 14.15 with a 400 watt linear, there's a colossal signal coming in. It could overload this second mixer. So that's one of the main reasons it went out of fashion. You've also got to be careful where you put that band. There's no real ideal solution to it. If you stick it covering a broadcast band, there's colossal signals and they inevitably leak through into the IF. So you hear all these broadcast signals on the amateur bands that aren't in the IF. So it's got good and bad points, but it's quite easy to build. The G0AMS receiver, anyone heard of that?
Yeah.
Very famous valve receiver from the early 60s. That was tunable IF. Right, so my idea on the bicycle was simple really. I couldn't buy 15 crystals for crystal oscillators because crystals were very expensive by then. They're ridiculously expensive now. But you can put a synthesizer in here and it only has to tune in, say, 0.5 megahertz steps. And a 0.5 meg step synthesizer is easy to build. You can make it really clean and low phase noise and all the rest of it. And you can see the sort of frequencies it has to cover for different bands. So 9 megahertz for 80 meters. 19.5 meg gives you 20 meters, 33.5 megahertz gives you 28 to 28.5, the bottom end of 10 meters. Right. Now, does that diagram, that's probably completely unreadable at the back, but it doesn't matter. So this is a simplified block diagram of this thing. So it looks quite daunting, but it isn't really. So there's an aerial. Now remember, this is a transceiver, so there's a PA and low pass filters and a directional coupler and switching.
Badenoch, 40. Braverman, 32. Hunt, 18.
Sorry about that.
Mordaunt, 60.
Let's not bring politics into it. So, on receive, the signal's routed through bandpass filter, first mixer, there's the synthesizer, bandpass filter, thank you Pete, 5 to 5.5 megs, second mixer with a VFO, all the same as the previous diagram, comes out, there's the crystal filters, there's actually 5 of them selectable for different bandwidths. Then on receive it gets routed through, there's an IF strip. I'm using Analog Devices chips that make really nice IF amplifiers. And there's AGC, I must have spent weeks on the AGC. It's a really difficult thing to make it work well. But I was happy with it in the end. And then you've got detectors, so there's a product detector for SSB and CW, there's a diode detector for AM, and there's a discriminator for FM. And then you switch whichever one you want in, and there's the audio chain. And on transmit, microphone, there's the speech processor, we all know about that one. We've all got a board at home for that. And then it's split, so you can feed the audio into the product, into this balance modulator for SSB or CW or AM. So for SSB it works as a balance modulator. If you want a carrier, you leak a bit of DC in, and that unbalances it. It's a common technique, the Japanese do it with some of their radios. And the signal comes through and it's routed back through this in reverse. These mixers are diode rings, so they work in either direction and so on. A few unusual things in this thing. I wanted everything to run off one reference, like a modern radio. So there's a 10 megahertz TCXO, and it's divided down, and the synthesizer's locked to it. The VFO has a counter, so that it's got the red display you can see, so you know what frequency you're on. That's locked to the TCXO. And the carrier for the balance modulator is 1.4 megahertz. That's a synthesizer, so that's locked to it. So the dial always reads, if the TCXO is spot on, the dial always reads correctly. And to set it up, you've only got one frequency adjustment, which is a little pot at the back. So you can adjust that and you know the set's all spot on frequency. There's a few tricks. So on receive, the 1.4 megahertz is used for SSB, and then there's a separate BFO for CW, so you can vary the pitch. I think that's about all I'll say about that. The band switch is an up and down toggle switch. And there's a little counter, and it generates a 4-bit binary code, which is fed round to everything that needs frequencies. So the PA low pass filters, the band pass filters, the counter gets offset so it always reads correctly on the right band. And it's also fed out externally for the linear amplifier, so that the linear amplifier is always on switches frequencies, you change bands. Does it make any sense? Yeah. So the controls are a bit odd because it's designed by me, and I don't have many Japanese radios, so I didn't try and copy any of them. I just thought I'll build it how I like to operate, because it doesn't matter, nothing else matters. So it's got things like the mode switch doesn't select the bandwidth for you. You can have different bandwidths in different modes, and some of them wouldn't work. So you can transmit SSB through the CW filter if you want. I don't think anyone would understand you. But you can do things like you can receive through an 8 kHz filter on CW. So that's your band, economy band scope. You can hear 8 kHz of spectrum all at once. So if the band's very quiet, it's quite good for scanning for signals. Readout shows the carrier frequency on SSB and the centre frequency on all the other filters. There's a spot push button here, and when you press that, it puts the product detector in circuit with a 1.4 MHz VFO. So if you're on AM, you can zero beat things. We've got a CW net on 2 meters, and our netting is terrible. We're always all on different frequencies. This overcomes all that because you can just zero beat it, so you can get within 20 or 30 hertz of an incoming carrier. Don't like PL259 connections, so it ain't got any. I put the Morse key jack on the front panel because the Japanese always put it on the back, whereas to me it's my favourite mode, so I plug Morse keys into different radios. And there's DIN sockets on the back for transverters and linear amplifiers and things like that. It's got a vague RA17 feel to it, the controls. Right, construction. How were the boards built? Any way I could think of, really. So the complicated boards are PCBs like the speech processor, things with lots of components on. They're all surface mount, laid out in KiCad, and boards etched in China. The PA's not got that many components on it, so that's sort of cut out with a scalpel from just copper clad. There's bits of Vero board for some of the audio circuitry. And it's built on lots and lots of circuit boards, so I can reprogram it by taking a board out and replacing it with another one. Screening was a problem. You've got lots of oscillators and signals, and they all mix together. The Japanese make radios with one huge board. How they ever get it to work, I dread to think. Probably lots and lots of iterations of the board. So I've cheated, and I've just put a lot of the boards that matter in screening cans with feed-through capacitors and little coax connectors. The case it's unusual. I couldn't think of how to make a neat case. So it's built out of sheets of aluminium. There's TST. Thanks, Dave. That's one of your bits of aluminium. And I bought some square section aluminium rod, and then I milled channels in it so that the lid all fits in the channels, and it's all just drilled and tapped.
The engine turning looks nice.
It's the sort of thing you see on antique sports car dashboards and the nose cones of 1930s aeroplanes and things.
Is your broom 6 inches shorter in the house, is it? You've used a bit of broom handle for it.
I spent ages trying to. You read about engine turning and people say, oh yes, you just use a brush, or you just use valve grinding paste, or you use bits of emery cloth or bits of sandpaper on a bit of broom handle. It's like soldering, everybody's got a method that works for them. I couldn't get any of those to work for me. I'd start on a sheet like that, and after about sort of 5 goes, you make it with a drill press. So you sit there with a drill press, and you move the sheet along, and you go bzz, 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 bzz. And of course, on a sheet that size, I don't know how many goes there are, but it's quite a lot. So whatever you use has to last that long. And it mustn't wear out significantly and start looking different at this corner to this corner.
Hence the 40 years.
I think that took about 20 minutes. Easy to do. It's supposed to stop it scratching. I could have painted it, but all my efforts with paint always end up getting scratched and flaking off, and I can never really get decent paint finishes at home. You could get it powder coated, I suppose, but even powder coating is not that brilliant.
What did you use in the end?
In the end, I've got a piece of aluminium and turned it, and you can get these abrasive blocks. It's like a foam rubber with sand embedded in it. And I could punch out with a hollow punch chunks of that and stick it in this aluminium tool, and that would easily do a panel like that. So that's how I did it, but it's like surface mount soldering. Some person says, well, I have to do it that way, nothing else works for me. And other people do something totally different, and that works for them. So
It looks nice and consistent.
well, it's reasonable, but you run out of patience after that. The first 100 goes.
A lot less messy than valve grinding paste, I'm sure.
Yeah. Again, I got some valve grounding paste. I couldn't get it consistent. It looked different on each circle almost. So I'm fed up with that. So I'll attempt to lift the thing up. So that's the innards of it. It's actually on 2 decks, so you're just looking at the top deck. I think I've got some slides showing that. So no, that's prototyping. So it started out with bits of board built like this. That's a received bandpass filter. I'm not suggesting that's good construction, but it's quick, and you can reuse the components afterwards. It's very good for playing. If you don't know what the circuit's going to be and you just want to play, it's a very quick way of building stuff. It's a sort of dead buggy Christmas tree style, using bits of old PCB bought from rallies. So if you look at these pictures, that's the PA. So that's the driver, which is all surface mount. That board's actually in the radio. That made it to the final radio. Then there's a sort of pre-driver. Right, that's a pre-driver. That's the driver stage. And there's temperature compensation here. And there's the actual power amplifier. These 2 transistors my boss gave me when I was at work for Technophone in 1988. Needed in my junk box all that time. And I thought it's a bit, they're 100 watt PA transistors really, so they're overkill, but they're 28 volts, so on 12 volt and 20 watts, they're indestructible. But you can see that's a typical lash up breadboard. This was originally one board, but this bit of it was a complete disaster, so I cut it off and made another one and then another one again, and eventually, with a lot of nerdling and fiddling around, ended up with something I was happy with. But it just illustrates the design process. It's not sort of, you don't just sort of sit and build it and get it to work, or not do not. Maybe if you're not clever than I am you can, but I can't do that. So there's a lot of testing going on. This was an early lash up of the whole radio. So there's 2 big sheets of aluminium which were gashed in my garage, which were already full of holes. And I thought, well, they're no great loss. So I just nailed everything to it. And the PA you can see is hanging off on a bit of heatsink. And there's the VFO, and that's the frequency counter. And there's some of the modules in cans, I think. That's the synthesizer. That's the transmit IF, receive IF. That's the speech processor. There's a bank of crystal filters, and so on. And it's built on these. I actually went on the Club 80 meter net with that. So what does it sound like? People say, oh, that's all right. So it sort of went through stages of work, and then eventually you get it to that form. What are we doing for time? 8:30, not too bad. That's shot to the construction of it. There's a lot of boards, and I'm trying to make it as small as I can. It doesn't look it, but I've worked quite hard to make it that small. So it's built in 2 sections really. This is the bottom, so that's the front panel. You're looking at the back of the front panel, and this is the base, and these 2 are the sides. So there's a layer of boards in there. The VFO's in the bottom because it's got to be very, very rigidly mounted. There's nothing worse than a VFO that's got backlash in it because it all bends. With rotary encoders, you don't worry about all that, but if you're doing it the old-fashioned way, you've got to have rigid mechanics. So this is about a 3mm aluminium plate to make it all rigid, and everything's bolted to it. Reference to that. You can see my awful wiring. I've never made a professional wireman, but it does the job. So that's the bottom half. So that's got the sort of 1.48 transmit and receive IFs, the audio amplifiers, the audio switching and all that sort of thing, and the front panel and the VFO. And then there's a sort of sub-chassis here. So this is the rear panel, and this sort of sub-chassis floats above that one on brackets. Floats on brackets, you know what I mean. So that's got the counter, the synthesizer, I don't know what the other boards are. That's the tunable IF section. That's the receive bandpass filters, and I think that's the synth. That's the transmit receive switch, and so on. So when it's together on these two pictures here, you can see there's the sort of bottom layer of boards, and this lot here sits hanging off these brackets. I don't think you could fly it in an aircraft, but I don't intend to. I think heavy vibration would kill it, but you can certainly sort of chuck it around a fair bit. It seems reasonably robust. So it sort of makes it a bit smaller than it would be otherwise. I'll talk a bit about the VFO, because a lot of people have trouble with VFOs. They say mine always drift, and it's not that difficult to make one that doesn't drift if you want to. You just need a bit of effort. So you've got to have very good mechanics. If everything twists and bends, and it will move, change frequency, and you sort of bang the bench and it sort of goes whoop, up, half a kilohertz up the band, which is most frustrating. There's a die-cast box. This is a dial drive off an Edison 358X wartime receiver, used in naval shore stations mostly. Had a very nice Edison dial mechanism. With a few modifications, I thought I could make that do the job. It had about the right reduction ratio. And then inside the box, you've obviously cuts inside the box. There's a capacitor off a G front end. Anyone know what G is? Clive's nodding his head, but I'd be surprised if he didn't. G was a wartime navigation system for bombers. The RAF, when they started bombing Germany, they couldn't get within about 5 miles of a target, which was a bit disastrous because they were losing thousands of men in the effort. So they came up with these electronic navigation aids, like forerunners to GPS. Worked in the VHF band. So part of my VFO may well have bombed Germany. That's something you can't say about an ICOM rig.
You tell the Germans that they're talking.
Funnily enough, I've never tried that. That's the circuit of the VFO, which I don't suppose anyone can see apart from me, but it doesn't matter. It's a Seiler oscillator, it's a coal pits with an extra capacitor. And I mentioned frequency drift. How do you stop it drifting? Because they can drift really well, VFOs. The trick is really solid mechanics, but control the temperature coefficient of all the components. So you've got these capacitors and an inductor. It's basically all that determines the frequency of a VFO. The circuit doesn't really matter. Everybody says, oh, the Vacar's much lower drift than the Hartley, and it's all bobbins. I had a Collins radio that had a simple Hartley oscillator, and it was amazingly stable. That was valve. It's nothing to do with all that. It's to do with the temperature coefficient of the components. So the capacitors start with something like NPOs, NPO ceramic. You can still buy them, which is a big advantage. And they've got a temperature coefficient that's quite low. Mica can be better, but it's a bit unpredictable from batch to batch. So I used NPO ceramic. So the capacitors are fairly low drift. The inductor always has a positive temperature coefficient, or at least every inductor I know about has. So as you heat it up, the inductance will go up and the frequency will go down. So you have drift. Don't use a Toco coil or anything to do with ferrite. Ferrite's a total disaster for drift. I mean a total disaster. Dust iron cores are better, air cores are better, but they've got to be rigid. So that's a T57 toroid, dust iron toroid. The 7 mix is supposed to be slightly lower drift than 6 or 2 mix, but I don't know if it makes much difference. So that's the starting point, and that gives you a fairly bad VFO. How do you actually make it drift free? Well, it turns out all you've got to do is get the temperature coefficient about right of everything. So I've got a little wooden box with a heatsink and some big resistors on it. There's a temperature chamber and there's a fan that stirs the air, and a very crude temperature controller. I put the VFO in there and I heat it up and I measure how much it moves with temperature. So you heat it up to about 40-50 degrees, depending more on the polystyrene insulation has melted in the box, I think. So you warm it up and it might move a few kilohertz up or down, and you make a note of the drift, and then you fiddle around with one capacitor. You have one capacitor that you make polystyrene. Now polystyrene has a negative temperature coefficient, about minus 150 part per million. It varies a bit from sample to sample, but you can sort of work out from the amount of drift what percentage of the capacitor needs to be polystyrene, and that's what you do. And then you run it again, and usually the drift is dramatically reduced. If it moved 15 kilohertz, it might move 5. You think, that's better, and then you think, if it went down in frequency, then you think, I've got too much polystyrene, reduce it a bit. You end up with a value, I mean, in there it's about, what have I got, 10 puff of polystyrene capacitor in it. And probably if I tried 3 different polystyrene capacitors, one of them would be have the right temperature coefficient to stop the drift. You can get it down to, say, maybe less than a kilohertz. And you find when you've done that, that the warm-up drift has disappeared all by itself. It took me ages to understand that. People go on about, oh, the warm-up drift, and it's nothing, you don't worry about it. If you get it stable with temperature, the warm-up drift takes care of itself. Because all the apparent drift when you switch the thing on is the thing warming up. So it took me ages to work that out. So that's how you make a VFO, if ever you want to make an old-fashioned VFO.
Will that change over time, or is that thing's going to deteriorate at that sort of the same rate, so one cancels the other out?
I think it's about 2 years old now and it's not moved yet.
Okay.
I've not put it in the temperature chamber and retried it, but I think it's going to be reasonably all right. I mean, it's not the end of the world if it does change a bit, but the ceramic capacitors I think are fairly stable. The coil seems to be. I mean, I know the values haven't changed because the VFO calibration's not moved. It hasn't sort of suddenly not been able to cover the bottom end of the band or something. So I don't think aging's a problem, but ask me again in 20 years' time.
Okay.
Further work. So I said it wasn't a complete station. So I built a 400 watt linear for it, which I can bring down and show you if you're interested. That uses MOSFETs. And that works well with it. That plugs into the back, and when you change bands on the radio, it switches the different low pass filters in, so you've got complete no tune operation, which is quite unusual for me because I'm used to valve rigs. Could do with an external VFO so that you could sort of jump between 2 frequencies for DX working, and maybe something a bit more accurate for digital mode if ever I get into them. There's no band scope on it, so I shall build a pan adapter, which is the old-fashioned way of doing a band scope with a cathode ray tube. And it doesn't cover VHF bands, so I'm using my FT480 on the 2 meter net, which is a blimmin' horrible radio for CW. So I need a transverter for it as well. Right. I think I've bored you enough with slides. Does it work? Well, it makes noises. This is 20 meters. So that's SSB filter. I can switch in a narrow filter or even a narrower one. I'm not going to find it now, will I? And I've got an audio filter if I'm desperate. Stop transmitting. So it's got decent CW filters. I can put it on FM and AM, and the chance of me finding an FM signal on HF is not very much at the moment. But yeah, it basically works very well. I've not really had any problems with it. It doesn't seem to suffer from overload or anything like that. Phase noise is quite good. I wrote a manual for it because I thought hopefully this will last me for some years, and I'll have forgotten how I built it in a few years' time. So there's a manual describing how it all works and all the test voltages and the gains of the different stages and what signals come out of the oscillators, and hopefully I can keep it running. Don't know what else to say about it really. Come and have a look.
You live very close to a medium wave transmitter.
Yes.
What sort of considerations did you have based on that?
Well, the only real worry I had was top band. The top band is obviously close to medium wave, so the front end bandpass filters, I could show you the circuit, I won't bother, but there's different circuit configurations for filters, and I picked one that rolled off faster on the low frequency side than the high frequency. So a lot of the filters are chosen for best image rejection. On top band, image rejection isn't a problem, but I was quite worried about what these broadcast signals would do. They're about minus 10 dBm coming out my aerial, which is a colossal signal. You can't light a light bulb off them, but it's not far off it. But it doesn't suffer any problems from them at all. So,
are they high order filters?
Are they? They're about 3 toroids.
Oh, okay.
They're all different circuits for doing to optimise the filters for different jobs. I could show you the circuit diagram if you're curious.
Oh, just intrigued
Yeah.
because that's got to be a consideration.
Yes. There's an awful lot of things to think about, I must admit.
And did you have problems with component tolerances and stuff, fake components? How did you source? Because I'd certainly with the toroids, it's a you buy something off the internet. It's God knows what you're getting. Someone painted them red with nail varnish or whatever.
Yes, I bought some toroids for a previous project, and they were T37-2s, so red ones. I've no idea, they had precisely the right inductance value. You put 10 turns on it and you got the right inductance, but the Q was about 3. And it should be about 200 for a decent toroid. So I've no idea what they were made from, but it wasn't it wasn't dust iron. But yeah, I did sort of every batch of toroids I bought in, I would measure one carefully. Semiconductors, I didn't see any fakes, I don't think. A lot of it was junk box components where possible, so it was stuff I mentioned. I bought a lot of bits from Fareham, and they tend to be quite good with their sourcing. It's not the cheapest way to buy bits. I've designed it around sort of fairly standardised parts, so I have sort of general purpose transistors I use for everything. There's nothing very exotic. There's some analog device chips in receiver IF, AD603s, and they're quite exotic. But most of it is just sort of TTL logic and op amps and diodes, and there's a lot of mains rectifier diodes used as switches. They make surprisingly good RF switches on the lower part of the band. The relays for the front end of the low pass filter, they were all thrown out at work. Stores threw out everything that wasn't associated with the bill of materials at one point. So there was this great box of stuff, and someone said, "Yeah, the stores are throwing out stuff, do you want any of it?" Those tubes are these beautiful Siemens relays that were ideal for RF switching. I've no idea what they were used for. They've probably been in the stores for 10 years. And that was 20 years ago when I acquired them, so they've been sat in my loft waiting for a project like this. But no, component purchasing wasn't a problem. It's built around bits I could buy. Because I'm not building someone else's design. If I can't get the bits, I'll use something else.
About things like the mixer and the products detectors, are they like the SPL type mixers, or are they discrete components you've used?
It varies. The ones at 1.4 megs are all discrete diodes and toroids. The two in the tunable IF in here, they're ADE1s, which again I had several of them kicking around in the junk box, came from a rally years and years ago. So the performance of those is a bit more important, and it's nice to buy something in, it's got a specification, you know what it should do. If you're wondering what the battery is, that's the band switch, so I can turn the power off, power switch, and it comes back on the same band. That was Andrew's idea. He said, so if you turn the power off, it comes back on a different band. He said, that'd be annoying. So, all right, I'll redesign the band switch, thank you. So great, it's very nice.
Is that part of your up-down counter, or is it?
Yes, so there's a little toggle switch.
Remembers that, is it?
Yeah.
Yeah.
So it's just TTL logic on a little tiny bit of board. It's very simple. It just steps through the bands.
So what were your main challenges? You mentioned about the AGC. So what were the hard bits? And what were
The AGC it's very easy to make AGC. It's very difficult to make AGC that doesn't make clicks and bangs and overshoots and all horrible noises. I spent weeks on the AGC. And I'd also got the experience of, I don't know whether the board that's been passed around is that had a tolerably good AGC on it. So I'd had loads and loads of goes at AGC. No, that's front end filters.
Oh, sorry.
Yeah, there's a bigger board somewhere. That's a tunable IF board, which has been hacked to bits. I built that in about 1992. It did get used as part of this one.
I built an AGC for my Bitex using an LED and an LDR in a bridge on the volume control. So the louder the audio got, the brighter the LED, and the more it lit up the light dependent resistor, and the more it turned the volume down. And that seemed to work. Very, very crude.
Yes.
But
Probably
that's
got a limited dynamic range though.
it has, yes, yes. If something's really strong, it's
Yeah.
the LED can only get so bright.
Yes. The PA drove me around the bend, I must admit. I've not done much with high power 20 watt semiconductor PAs, and I could make it work brilliantly on several bands easily, but to make something that was linear on all the bands took me a long time. I really struggled with that PA.
What class amplifier is it?
It's AB, it's nothing clever. It's just two MOSFETs in the circuit up if you like. Should have circuit diagrams in here somewhere, or maybe not. Ooh, bollocks.
I may have to stop recording in a minute. My phone's getting almost too hot to touch.
It's done well.
You've got another 37 hours.
Well, I don't know about that. So
If
you'll
I
be
bought-
fried egg on it in a minute.
What was that? Oh, of course, it's over here. Sorry, I'm confused by two screens. So, no, that's not going to work. Where's the PA? PA circuit diagram, let's bring that up. I wonder if it's visible. No. This thing won't magnify very easily. How do you make it bigger? No. Oh.
Dots, 3 dots.
3 dots.
Right.
That's it. So the PA, no, it's not going to do that. So it's very simple. There's nothing to it. The difficulty is getting it to blooming work. Get rid of that thing. Don't know why that came up. So you've got these two MOSFETs. As I say, I've had those since 1988. They're junk box parts. I think they were meant for Raven, which was a project at Plessy for a tank radio. The transformer here is a compromise. It's got to match 50 ohms at this point, down to a few ohms on the drain of the FETs, and that's really hard to get right. And you can make them work brilliantly at the bottom end of the band or the top end of the band, and sometimes the bottom and the medium, but you never get all three, and you struggle. I ended up with the old brass tubes around a ferrite thing. It's a standard design, but I fiddled and fiddled and fiddled with that. I tried different MOSFETs, all sorts of things. The impedance on here is critical because you get the waveform on the drains when this is going at 20 watts, so there's not a nice happy sine wave, and it feeds back via the capacitance into the gate, and that causes all sorts of weird effects. It took me ages to work out that was going on. I probably could do a better PA now, but yeah, I struggle with that. That took me a long time. I struggle with lots of other bits as well. I mean, things like the transmit receive switch, I started with pin diodes and different types of relays and read relays and all sorts of things, trying to find something that would sort of meet the switching requirement for braking, which turns out I never needed anyway, and didn't burn out in a hurry and all the rest of it.
How much simulation did you use?
Some things simulate well, filters simulate fairly well. So the received bandpass filters I could simulate. Some of the little amplifiers and things I could simulate. Oscillators I don't usually bother. I do sort of simple calculations and simulation for oscillators I don't really think is much use for me. Digital stuff I just do. Don't need to simulate that. It just does what it does. Some of the audio filtering and things was simulated. But there's some surprising things like the PA low pass filters. They're all designed with a simulator, and they were all presented a nice 50 ohm match to this point here. Didn't work. Why didn't it? It worked beautifully with a 50 ohm load on here. And of course, the reason is the harmonics from this thing are only 10 dBs down, which is why you need a filter. And all that harmonic energy goes out of here into the filter, and it gets reflected back into the PA. Yeah. Obvious when you think about it. So what matters is the impedance that the filter presents to the PA at the harmonic frequencies. So it took me ages to work out what you needed was L input filters sometimes. And it's a bit hit and miss. And I look at other people's designs for mostly for big linears, and they do all sorts of weird things with their filters as well. So they've obviously had the same problems, but not very well documented. Any more questions?
On your frequency counter,
Yeah.
is it literally just a frequency counter that counts the VFO? It's not, there's no synthesis goes on at all, is it?
No, it doesn't try and stabilise the VFO.
Yeah.
It's got a big diode matrix, so you've got this band bus. So there's a board here that generates 4 bits. So band 0 is top band, band 1 is 80 metres, and so on. I think it's up to 13 bands. And that gets routed all around the radio. So different filters switch in for different bands. Some filters cover 2 bands, and so on. Synthesizers got to be reprogrammed for each band. And the counter has to subtract different numbers. So if you look at the display, it reads, well, on 10 metres, it reads 29.529. So to know it's 29, it's counting the VFO, which isn't changing from band to band. So there's this big diode matrix, you can see it here, this big rack of diodes, and it works out what numbers got to be subtracted from the count to make the dial read correctly. And it also has to count backwards. Because of the tunable IF scheme, the VFO tunes backwards, so it's higher in frequency for the lower end of the band.
My goodness.
Couldn't you have done that as software?
A better person could, but my software skills are negligible. So the other thing is, I wanted everything to be electrically quiet. The set's got virtually no sprogs on any band, so it's all very simple stuff. There's microprocessors generate a racket as a rule of thumb. Right, if anyone wants to have a play with it, they can. It can't transmit. I've only got a little 1/2 amp power supply on there at the moment to cut the amount of weight I had to lug up the stairs, but you can use it on receive.
Fantastic. Thank you very much.
Can I borrow for a week?